I could put the protector on. Things are going all right?
Yep.
It goes. All right. Well, let's continue on with our discussion of matrix arithmetic. Last time we talked about how we can do matrix addition, subtraction, multiplication, and talked a little bit about how we can rewrite a system of linear equations as a matrix equation. And we'll talk a little bit more, probably today, but maybe Wednesday, about how we can use that matrix equation to solve a system in certain cases rather than having to do row reduction. Well, we'll start to do row reduction in some sense. But another way to solve a system of equations using what we refer to as the inverse of a matrix. Before we get there, we want to verify some properties of arithmetic that we think might be true as far as matrices go that mirror the ideas of what we did back in real numbers. So that's what section 2.2 talks about. So move this out of the way because I'm gonna hit this thing, I'm sure, with my hand. When you're working on the homework that I gave you, what did I not spell today? Oh, this property of matrix operations anyway, as the title of the section, but I'm leaving it. In the homework I gave you, you'll notice it's a little bit more of a proof flavor than it is a computational flavor. There should be computational problems in WebAssign over these particular sections. I believe I'm going to try to remember to tell you in class when I make the due dates. What I try to do with due dates is if we finish up a section, I'll give a class period lead time in between on WebAssign. So if you've got questions, you can come ask me, and then have it do the Tuesday, Thursday, or Sunday after that. So, but I believe I've got the due date for 2.1 set for this Thursday, actually. So, I think that might be the last one that's actually set. So I'll set the next one, and I'll try to remember to announce when that is. If you've got questions, just email me. I'll make sure that I tell you. Hello, how are you?
Good. How are you?
Good. Yep. All right. Anyway, you'll notice that the homework that I just gave you has a little bit more of a proof flair, whereas I'll leave for the WebAssign more computational problems. Okay. There'll be a little bit of a proof flair in this particular section, but like I said, one of the things I want to do with the homework more is making sure I'm giving you feedback on the proofs that you're doing, and not so much on the computational things. I'll let the WebAssign give you the feedback on the computational thing. Of course, you can always ask me, but that's my thought behind this. If you don't like it, come tell me. We'll figure out changing it. Okay. All right. Anyway, so some of the types of problems some of the types of properties of arithmetic that we're interested in again are going to mirror ones that we talked about for real numbers. But we've already seen one that doesn't work, right? We said that matrix multiplication does not work in both ways, generally speaking, right? AB is not necessarily equal to BA. Okay. But however, there are a number of different properties that do hold. So they just go through a whole bunch of them. We'll write many of them down, but we won't prove all of them. So the first one they talk about, this is on page 52 of your text. The first one they talk about is the fact that matrix addition is commutative. You can add in either order. Of course, in order to be able to add two matrices together, what has to be true about the two matrices? What do they need to be? Same size, right? They have the exact same dimensions, otherwise you can't add them. I didn't write it down. They do write it in the text. Anytime that I'm going to write this, assume that you are able to do the operation. Okay? If you cannot do the operation, then it's just undefined and you go on with life. Okay? So when we're going to prove these properties, we want to make sure that we're talking about matrices that are actually conformable with respect to the operation, meaning that we can actually do the operation. All right, so let's just go through how a proof of this would work. So when we start proving some of these with with matrix arithmetic, we have to appeal to the general entries. We said that a matrix is equal, two matrices are equal only if all of their entries are the same. Okay. So that's typically what we do when we show properties of arithmetic. We're going to look at what a general entry has to look on the left-hand side, what a general entry has to look like on the right-hand side, and then argue that those two things have to be equal to each other. That's the way we're going to do this. Okay. So to start this off, and I'll do this one because it's pretty straightforward how we're going to do it. They'll get a little bit more complicated as they go along. None of them are horrible if you just follow what the rules are for your arithmetic. All right, so let's let A be the general, a matrix of general entry A sub ij. And here, just to emphasize that everything's going to work correctly, I'll denote that A is an m by n matrix, and we'll denote that our B is also an m by n matrix, and we'll say it has general entries B sub ij. So you just told me that a minute ago that the matrices have to have the same size, so I'm just denoting that with our little subscript notation. Now, like I said, I think it's just easier, at least in my mind, it's easier to work on one side of the equation until you write things in terms of the matrices you started with. Work on the other side of the equation, do the exact same thing, and see that you end up with the same general entry. Okay? So let's do that for the left-hand side. What size is the left-hand side going to have? If I add two m by n matrices together, the size is going to be the same. Good. I'll write it as m by n. I'll just start with another letter, c sub ij. But how do we get the entries for the sum of the matrices here? How do we get the entries of the sum? What do we do? Yeah, you add the corresponding entries together, right? So I'll just start right down where c sub ij is equal to a sub ij plus b sub ij. Okay. All right. That's an I and a J. It looks really bad. It looks like a half winking smiley face or something there. All right. This is what I meant when I said a second ago, I'm going to work on one side of the equation until I get it down to the entries of the matrices that I started with. So here I've written my entry of my arithmetic operation in terms of the matrices that I started with. Okay? So I'll stop with the left-hand side, and now I'll do the same thing with the right-hand side. Okay. Oops. I just said do the right hand side, and I started to rewrite the left hand side again. All right, so we'll do the same thing with b plus a. I'll give it a name to start with. How is our d sub ij going to be defined here in terms of our original matrices? So in this case, we're doing b plus the a. So what should we have for our general entry now? Yeah, because again, we match up entries and add them together, right? Now again, for our purposes, everything here, every entry of our matrix is going to be a real number. Perhaps later on this semester, we'll use complex numbers every once in a while. We won't do that much. In particular, though, we're using numbers that we can add in either order. All right, so our a sub ij and b sub ij are here just regular old real number arithmetic, or regular old complex number arithmetic. So what do I know about the a sub ij plus b sub ij, and then the reverse, the b sub ij plus a sub ij, what's true? Yeah, they're the same, right? Okay. So since a sub ij plus b sub ij is equal to b sub ij plus a sub ij, we have that c sub ij must be equal to d sub ij. And again, if we're going to show that two matrices are equal, we want to show that they have the exact same entries. We used c sub ij to denote the a plus b. We use the d sub ij to denote the b plus a. They have to be the same. So therefore, A plus B must be equal to B plus A. All right, I know this one was, well, hopefully it was pretty obvious of why they were true in general, but I wanted to go through this one in a little bit more detail because I wanted to show you the process that we're going to use in order to show the two things are equal. Questions on that one? So you would do the same plan of attack to do any of these matrix arithmetic proofs. So the second one says that matrix addition is associative. You would go through this one just like we did the previous one, except that instead of starting with two matrices, I would have three. Do an A, and a B, and a C. Okay. So let's run through this one a little bit more quickly than we did the last one, but it's the same idea. So again, in order to be able to add these three matrices together, no matter how you're grouping them, what has to be true about all three matrices? Same size, good. All right, so we're going through and the only part that we're doing, the only reason why we're doing this part is because we're just trying to get a way to reference a general entry for each of the three matrices. Okay? So that's the only reason why we're writing this part down. Now, the good news is that once we get past the arithmetic kind of stage of this, a lot of our proofs will no longer be going back to the individual elements of the matrices and trying to prove things. Okay. So it's kind of like, it's not unlike what you do back in calculus, right? You do the derivatives the hard way, and then you have shortcuts and do things the easy way, right? We're going to do proofs right now that involve digging around in the elements of the matrix, because we don't really have much to work with except for how we define the operations, right? But once we start getting some properties of matrices, we won't have to dig around in the entries as much. We'll be able to do proofs with just talking about general matrices instead. Okay. But it's also, if you've had discrete, remember we had to do set proofs, we had to dig around with the elements. It's kind of that kind of flavor as well. Given a discrete, you can ignore what I just said. But it has that same flavor as well. All right. So again, same premise that we used last time. I want to work on the left-hand side till I get an entry down in terms of the matrices that we just defined. Then do the exact same thing for the right-hand side, and hopefully they're the same. Okay. If we're working on the left-hand side, which of those two, given the grouping symbols, which of those two operations would you do first? The B plus C, right? So, again, give it a name. I'll call it D sub ij. How is D sub ij defined? Good, yeah. We're adding B and C together. Oh, hey. We're adding B and C together. If I could write today, that would be amazing. So the D is in terms of the B plus C. Now notice that I'm not all the way down to, well, A, I haven't done all the way to the left-hand side period because I get three matrices. And I'm certainly not down into A, B, C for my general entry, right? So now what we add together next? Once we've added B and C together, what gets added? The A. I just keep going through the alphabet. I don't like using E because E has a different connotation. So I'll use F next. Call it F sub ij. Now, how is notice at any particular stage here, I'm only adding two matrices together. So working with just A and treating B plus C as a single matrix, how would you define your F sub ij? Good, yeah, the A sub ij plus the D sub ij, right? Adding those entries. Is there anything that we can substitute in now? What did we just say in the line above that D sub ij is equal to? Yeah, the B plus the C, right? And I would have parentheses around the B sub ij and the C sub ij part. So I'm plugging that in for the D. Okay so far? Okay. So now this is where I was talking about. We're now down to the general entry of the left-hand side being in terms of the matrices that we started with. Right? So now I'll stop and I'll work to do the exact same thing on the other side. Okay? On the other side, which addition should you do first? The A plus B? Okay, going down the alphabet, I'll use a G for that one. How is G sub ij defined? Good, yep, we're adding the A and the B together, so it'll be A sub ij plus the B sub ij, good. What gets added together now after we do the A plus the B? What gets added? The C? Yep, good. So now if we stick the C on the end, should be the last letter I have to use. I'll use an H. After H, I'd have to go to, well, probably K next, right? Because I've got I's and J's representing subscripts. I don't want to use K either, because here in a minute we're going to use it for a different subscript, so I go all the way down to L if I were going to just do another one. Okay. All right. Now again, in terms of those two matrices, what two entries are you adding together to get A plus B plus C? Yeah, the G sub ij and the C sub ij. Good? And then again, just like we did in the previous step, is there anything that I can substitute in for one of those two entries? Good. The G sub ij is the A sub ij plus the B sub ij. Cool. I know, it's a lot of writing. That's basically how these proofs go. It's a lot of writing, a lot of just put in the definitions and follow your nose. All right, so now at this step, we've got the right-hand side in terms of the entries of the matrices that we started with. Okay, so we got left-hand side in terms of A, B, and C, right-hand side in terms of A, B, and C. Now I want to argue that they really are the same. Okay. Well, notice here again, what we've got here are statements about real number, complex number, whatever, addition. What do we know about real number or complex number addition? It is associative, right? We can regroup. So we can say since A sub ij plus the quantity B sub ij plus C sub ij is the same thing as the other way around, we're going to have that our G sub ij is equal to H sub ij, which is exactly what we wanted, right? We agree? It's exactly what we want. What's that?
I think it's F.
Oh, it's F. Thanks. Sorry. Then no, we don't agree with me. That's what we wanted. Thus, we must have the result because the general entries are the same. Questions on that one at all? Again, these are how these proofs go. At least that's how I typically do them with students. You can probably write it in a slightly different fashion, but generally speaking, this is how they go. Work with one side until you get down as far as you can. Work with the other side until you get it down as far as you can. And then argue that those two things have to be the same. What you do not want to do is try to do both sides, something to both sides of an equation. You don't know the equation's been established yet. Okay. You can't work on both sides of an equation. You can't do something to both sides of an equation without the equation part. Okay. There's not two sides yet. Does that make sense? Okay. Any questions on that one? I know, not the most interesting thing in the world, but it is a good proof technique teaching tool. So we go through it. All right. So let's just write down a couple of the other ones. I'm not going to prove all of them by any stretch of the imagination. The third one that pops up in the first theorem of the section, I'm trying to number them the way they're numbered in the book, talks about the way that scalar multiplication is associative. Now, the other two, well, this probably isn't very surprising either. The other two aren't necessarily surprising because we know that when we define addition of matrices, we're just really digging into the elements and adding there, right? And the addition in each of the entries is commutative, so we would expect that for the whole matrix, right? However, here something really different is going on. If you look, there's two different types of multiplication we're talking about. This, when I do C times D and write it with lowercase letters, I'm assuming my C and D here are scalars, which means that we're really just multiplying two real numbers together. That's just regular old real number multiplication. But this is take a number and multiply it by a matrix, right? On the right-hand side, notice I don't have real number multiplication going on, at least the way it's written. This says take a scalar times a matrix, I get a new matrix, and then do it again, okay? So there's really different multiplications going on the right-hand side than there are on the left. Okay. Now again, we know that it's really going to boil down to the fact that real number multiplication is associative. But generally speaking, there's two different multiplications going on. This is why it's something to check. We're going to see this later on when we start talking about what are referred to as vector spaces, where scalar multiplication may not look like what scalar multiplication has been done before. Things will get a little weird. It's math. Of course things are going to get weird. That's what it does. You get past calculus, math goes to hell. It just goes everywhere. Okay. All right. That's when the fun begins, though. Got to figure things out when things start changing definitions or start changing what you were assuming to be true and see what happens. That's the fun part. Okay, I think it's a fun part. All right. If I didn't think it was the fun part, do you really think I'd be doing this job? No. I would have chosen my job very poorly. Okay. All right. The fourth one, again, one of the reasons why they mentioned this one is because it's leading us into this vector space idea. This really is the number one that I wrote here. The scalar one's why I wrote it fancy, so you know it's a one with the rest. It's supposed to be just putting a vertical bar there for a one. So if I do the scalar one, multiply it by a, I get a back again. Not that this is earth-shattering, because you're going to take the number 1 and multiply it by each entry, and it doesn't change any of the entries. The idea behind this is that when we do this particular scalar multiplication, it really is preserving a scale, right? We're not changing what a unit is. Okay. Again, this is important later on when we start talking about vector spaces. So even though it looks like a pretty easy property, and it is a really easy property to prove and understand why it's true, it does have conceptual applications later on. So that's why it's listed there. The other ones are talking about distributive properties of scalar multiplication. So one says that scalar multiplication distributes over matrix sums. The other says scalar multiplication distributes over number sums or scalar sums. They look similar, but they really are saying two different things, because here you're adding two matrices together, here you're adding two real numbers together. That's why it needs to be two separate properties. It looks the same, right? It looks like distributive property. That's the reason why it's written two different ways. All right, so these are all the arithmetic properties that pop up using scalar multiplication and addition, and we're going to do matrix multiplication here in a second. But are there any questions about how you would prove those last ones? Same idea as what we did for the sums. Okay. They do this one, number 5, in the text. So you're going to go see what number 5 looks like in the text. You can. It's good ones to practice on because they're pretty short to do. So they're good ones to practice through and make sure that you're understanding what's going on. The multiplication ones get a little bit more complex as we go forward here. All right. One of the other things they do in this section is start to introduce some special matrices. So one of the special matrices they denote is the zero matrix. We need a different zero matrix for every size that we have. So we'll denote it with a capital letter O for obvious reasons. If we needed to make sure that we know what the dimensions are, we'll put a sub m by n there. But if it's obvious from context, we won't write this part. We'll just write an O for the zero matrix. Okay. So the zero matrix is just, I should say the m by n matrix here. In which every entry is 0. We need a zero matrix defined, just like we need the number 0 defined. One of the things that most of algebra comes about by trying to solve equations. Trying to solve equations gets back to isolating a variable. So if you want to solve the equation, for example, x plus 3 equals 5, we technically add the opposite of 3 to both sides, right? The additive inverse. When we do that, that's because we undo the addition by 3, but when we do that, if I take the 3 plus the negative 3, I really get a 0 there, right? So I need to make sure that I know that x plus 0 is x. Okay? That's why we have the number 0 there from algebraic purposes, so when I add 0, it doesn't affect the number at all. Same idea with matrices, why we need a zero matrix. So it's not a hard concept to understand what the zero matrix is, but from an algebraic standpoint, it's important to have what we refer to as an additive identity. The thing that when we add to it, we don't change the number at all, or change the matrix at all. So that's why it's important to have the zero matrix defined. They give you a couple of other properties that you would expect with zero matrices. This is the next theorem. I'll just write it as properties of zero matrices. Again, the whole point is that if I add the zero matrix to any matrix, I get A back again. Again, I'm being a little lax with my notation here. In order to be able to add these two matrices, I need to make sure that A and 0 have the same size. So whatever the size of A is, I'd have to use the appropriately sized 0 matrix. But just to save me time from writing down a bunch of notation, I think you're okay with the fact that I have, if I'm going to add these together, I have to add things of the same size. You already told me that to start all of this off. Okay. All right. If the other property that's fairly straightforward, and this is the idea of being able to solve things, is that if I take the additive, if I take -1 and run it through A, or do the opposite of A and add it to A, I get 0. And that was the whole idea that I talked about before we even started this. If you're trying to isolate something and you add its additive inverse, you technically have a 0 left, and you need to make sure that when you add the 0 back, you get 0 again. So that's what we're talking about here, is that we really do get the 0 if I add the additive inverse. That's just a statement about additive inverses. These are algebraically important. They're not horribly interesting results. Okay. Again, a lot of these pop back up when we're talking about vector spaces, which we'll talk about later on in another chapter. If you have a scalar times A, and this is actually going to be important later. If I have a scalar times A and I get the 0 matrix, then either the scalar is 0 or the matrix is the 0 matrix. It's important here that I've got the scalar times the matrix being 0. If I have two matrices that are equal to, and a product is equal to 0, we don't necessarily get that one of the other matrices has to be 0. There's not the 0 factor property doesn't hold for matrices in general. We'll show an example of that here later. But for scalars, it works. So either the scalar had to be 0 or the matrix has to be 0. Let's prove that last one just to see how that would go, only because it's an interesting proof technique. So I need to prove an OR statement. Typically, when you prove an OR statement, you'll show that it's true if the first condition is met, and then assume that condition is not met, and then prove the other one had to work. Okay. Typically call it proof by cases. Okay. If case 1 is true, what happens? Well, if the C is equal to, well, actually this is not true. We're going to assume this part. If, and we'll assume that the C is not, sorry, I said that wrong. When we want to do an OR, typically what we'll do is we'll say, well, if one doesn't happen, the other did have to happen. I didn't lie about that part. I just said something wrong at the beginning. This is what we're assuming. We have to show one of these two things, right? Well, either C is 0 or it's not. If it is 0, then that was the result, right? So let's assume that it's not, and then show that A has to actually be the 0 matrix. Okay. All right. So we'll suppose that C times A is equal to 0, and the scalar we're using is not 0. Because if the scalar we're using is 0, then we're done. There's no point in anything to do. Again, here, let's let A be a general matrix. I wrote the dimensions here, but since I'm not working with any other matrix, I don't really need to worry about writing this part if I want to be lazy, because there's only one matrix. What's going on here? All right, I want to show that when I do C times the A, I get well, sorry, I want to get that these. I want to show that all of these a sub ij's are a 0, right? When we do scalar multiplication, how do we do scalar multiplication? How does that work? What do you do with the scalar? Multiply by every single entry, right? So your b sub ij here is going to equal c times a sub ij, right? You agree? But what are we assuming about c times a? What are we supposed to get? When we do c times a, what are we assuming is true? It's the 0 matrix, right? So what does that c times a sub ij have to be? 0, right? Okay. And again, that last equality is because we're assuming, right? We're supposing. I like to use assume when we're doing proof by contradiction. Because what happens when you assume? You do a proof by contradiction that usually leads to a bad thing, right? A contradiction. So that's why I try to use assume there. Here we're supposing, we're assuming that, or we're supposing that the c times a is equal to 0. All right. What else are we supposing here besides the fact that the product is equal to 0? What are we assuming about the c? It's not 0. Well, if the c is not 0 and we're doing real number multiplication, then the a sub ij has to be 0, correct? If the general entry, no matter what the I and j are, is 0, then the matrix has to be 0. So again, the reason why I went through this particular proof is because of the proof technique, not because of the fact that the result is all that interesting. When you're trying to prove an OR statement, negate one of them and show the other has to be true. Because if it's an either or, well, it could be both, but if it's an OR statement, if the first part's not true, then the second part has to be. So that's a pretty technical technique for proving an OR statement in math. Negate one, show the other one has to follow. That's why I did that one. Like I said, it's not because the result's all that interesting, because it's not something that we. If I'm going to end up with a bunch of zeros when I'm done, and all I'm doing is multiplying by a scalar, I either been multiplied by 0 or they're all 0 to start with. All right. Questions on that one at all? All right. Well, let's go with the ones that are a little bit more complicated, and those are the ones that have to do with matrix multiplication. Pardon me. So remember that when we multiply, we talked about this one last time. We had something like this. Remember how we multiply. What has to be true about the dimensions again? Right, the columns of the first have to match the rows of the second, right? So we can do that matchup. So in general, notice in this case, we would do the 1, to get this upper left-hand entry, we would do the 1 times the 4, the 3 times the 1, and the 2 times the 2, right? We take the row and we match it with the column. Okay. Notice when we're getting the 1, 1 entry, we're using the row 1 entries of the first matrix and the column 1 matrix of the second one. And the thing that's changing are the columns of the first and the rows of the second, right? Agree with that? Same thing, and I'll write out the second one. We would, in this, with the 1, 2 entry, you would have 1 times 1, 3 times 6, 2 times 6, right? And the other two would be similar. But notice what changes. We're changing what column we're in the first one at the exact same time as we're changing what row we're in the second one and multiplying together. And then the entry that we get is what row we're working off of in the first matrix and what column we're working off of in the second matrix, right? So here's how you can write a general, and I'm not going to fill out the other two, but when we do a general entry of a product of two matrices, well, remember that overall, we're doing a sum, right? We're adding things up, so I'll use summation notation. What changes as you go, I'll call it a K. What changes as you go are the columns of the first and the rows of the second. So I'll write this as A sub ik, B sub kj, where our A will be an M by N matrix, and B will be an N by P. N by P. Okay, just to emphasize again, we're running across the row. The column number changes as we go for the first one, right? Here we're running down the column for the second matrix. That's why the K is there. That's the thing that's changing. What we end up with is the entry that's in the row I, column J position. So again, here was row 1 for the first matrix. Here's column 1 for the first matrix. This one is row 1, column, that's a 0, I don't know why I wrote 6, column 2, right? All right. What size matrix do we end up with when we're done? M by P, good, yep. So again, here I'm making sure that my columns and rows match here, right? And then we end up with M by P. So again, when we do this general entry piece here, it looks a little strange. It's a little harder to work with sometimes. All right. But along these lines now, we can do our properties of multiplication. Oops. The first one just says that matrix multiplication is associative. The second one says that multiplication distributes, a multiplication on the left distributes over a sum. And the third one says that multiplication from the right distributes over a sum. Notice in this case, I really did have to write two properties. Oops. It helped if I actually put the extra matrix in there. Notice in general again that this one, where I have A times B plus C, is not the same thing as B plus C times A, generally speaking, right? Matrix multiplication does not commute. Okay? So again, I have two different properties. Now, number 2 here, I have a video on Moodle posted, so you can see that one, going through that one. This one's on your homework, if you've noticed. Okay. So, we'll do the first one here, at least get started on it here in a second. The last one talks about that scalars get to move wherever you'd like them, which is not a huge surprise. So if you have the scalar on the outside, I could put the scalar with the first one and then multiply by the second. Or if I want to be fancy, I could put the scalar with the second one and then multiply by the first on the left. That last one shouldn't be a huge surprise because, again, how do we define scalar multiplication? You just multiply it all the way through everything, right? So all this is saying is, okay, I can multiply the matrix together first and then send the C through everything. Or I could just send the C through A and then multiply. Or maybe B has a bunch of fractions in it and C will cancel, and so you'll send the C through the B and then multiply. Ooh, I actually pointed at it. I didn't know look at it. All right, so let's see if we can go to the first one here, or at least get started on it, and we'll probably have to finish it off. Like I said, 2 is on the video on Moodle. 3 is what I'm asking you to do for homework. Okay. Well, and not only is 2 in the video, 2 is also done in the book for you. All right, so let's let A be... What's wrong?
Oh, that's a part.
Yeah. Let's let A be m by n. We'll let B be n by p. And we'll let C be p by q. Notice I need to make sure that my n's match for my A and my B, because the A times the B will get multiplied together. And I need to make sure my P's match, because my B and C get multiplied together, right? What size matrix are you going to end up with when you're done? Be M by Q when we're done, right? Okay, so now let's work with the left-hand side. If we're going to work with the left-hand side first, which product should you do first? Yeah, the B and the C, right? What size will B times C have? N by Q, good. Number of rows of the first, which is N. Number of columns of the second, which is Q, right? Can I get this all on the screen at the same time? What is my entry going to look like? So again, looking back up to that right there, what's my entry going to look like? What's your upper limit of your sum going to be? Well, notice up here, where'd this n come from? It came from that, right? So what's it going to be here? It'll be the p, right? It's the pieces matching in both of them. Here's a p and here's a p, right? So it'll be p here. I know I'm out of time. What's going to go on the inside? Good. Yep. Good. KJ. Good. So yeah, the K, remember the middle piece is the one that's changing, right? I'd like to think about it as the middle, the columns are the first, the rows are the second. All right. See if you can figure out, at least for the next time, see if you can figure out what the A times the B plus divided the P times C will look like. And then we'll do the other way around as well. Finish that off next time. I know, it gets complicated. We'll see you on Wednesday, if not before. What's that? That's what I have right now. I might move to Monday. We'll see how Wednesday goes. I'm leaning toward doing it Monday. We didn't get as far as I thought we would.